Structural analysis is commonly done using analytical method. For simple static structural analysis, for example, we can use the equilibrium equation to calculate the reaction force and bending moment, and then from that reaction we can calculate the stress and also deformation out of that structure. Let's take a simple example. For example, this simple beam is constrained in the both ends. Then we also give two loads over the beam. From here we can calculate a specific point. For example, in this point we want to calculate the stress. We can calculate it from the moment and the force reaction. From here we can get the tensile and also the shear stress, for example. But in the real world application, it is often the structure is not that simple, so the analytical result itself cannot be used anymore because it cannot be solved analytically. Then engineers use the simplified method by dividing the beam into a certain element or certain number of elements, also called the finite element method. For each element in its sides, it has some nodes, and collectively these elements are called mesh or grid. The element itself not only in the form of triangle. For example, we have another form such as square for the two-dimensional, and we also have another form in the three-dimensional, and we also have the one-dimensional element, for example like bar or beam element. Now let's take a deeper look for the simplest form, which is the bar or the beam element. We can make the analogy for this by using the spring analogy. Let's say we have a spring, then we pull it with the force, let's say F, then this spring will be deformed from the initial position X become the X plus dx. Then from this simple stretch we can use the equation F is equal to the K times dx, which is the K is the stiffness. With the same analogy, we can also arrange the same equation for our node, with the force and deformation are in the vector form and the stiffness is in the matrix form. From our two nodes, we can set 6 degrees of freedoms. Let's say two translation in the x direction, 2 translation in the y direction, and 2 rotation motion. So we can arrange the equation to become matrix like this. We can say that this matrix has 6 degrees of freedoms. We can imagine more the nodes or the dimension of the element, we have more degree of freedom. Now let's say every element have its own matrix, stiffness matrix, and if we arrange it in some elements, we have, for example, 3 matrices, and we can arrange it into new single stiffness matrix, which is of course bigger and has more degree of freedoms. And then to solve this matrix, we must apply some boundaries, or called the boundary conditions. For example, the deformation and also force at certain point or nodes. From this, we can calculate the reaction force and deformation. Then we can get the specific data that we need. For example, the stress distribution to get the maximum strength of this structure, and also the deformation to calculate its rigidity. But we know that the equations has a lot of matrix which we cannot solve manually by using hand. So the first project to do this calculation using the computational method was from the MSc company in the NASA structural analysis project, or called NASTRAN, and then this product become MSc NASTRAN. Of course, it is not only for the static structural analysis, it is more than that. For example, nonlinear analysis, thermal analysis, buckling, and much more. Now, this commercial software is become widely used in a lot of industrial applications and become new standard for designing mechanical parts.